So problem 4 on our last problem set is a little bit different than the other antiderivative problems in this problem set because it begins not by giving us the first derivative of a function, but it actually gives us the second derivative, the derivative of the derivative. And so to get to where we're going on this problem, we're going to have to go through a multi-step process. We're starting out with f2 prime, and then taking an antiderivative of that is not going to get us f, it's going to get us f prime, the derivative of f. So we have to do it again. So that's kind of the schematic behind what we would have to do on this problem. So this will be good practice for us in finding antiderivatives and using these initial data to figure out the values for their arbitrary constants. So this will be good practice for the exam. Let's take this first step. If I have a function whose derivative is 20x to the third minus 14, then how would I find an antiderivative for that, 20x to the third minus 14? So the power rule for antiderivatives tells us to add 1 to the exponent. So my exponent's going to go from 3 to 4. And then divide by that new exponent. So the x to the third in this function becomes x to the fourth over 4. That 20 that's out in front comes along for the ride. So the first term in my antiderivative is 20 times x to the fourth over 4. Might be a good idea to simplify that. I'm going to do that right now. The 20 divided by 4, we can write as 5. So there's my first term, 5x to the fourth. And then what happens with the minus 14? Yeah, exactly. Because there's secretly an x to the power 0 sitting in front of this 14. We could sketch it in there if we wanted to be explicit. Right? And so we apply the same power rule, increasing the exponent by 1 and dividing by that new exponent, which is 1. But that's just going to make an x to the first power over 1 up here. And so I get minus 14x. But this antiderivative is still lacking something. What am I missing? Yeah. And that plus c is actually really important in problems like this one because they're not asking us for just any antiderivative for this function. They're asking for a particular antiderivative that satisfies a condition, f prime of 0 equals 2. So without this plus c, we're not going to be able to satisfy that condition. We're not guaranteed that that's going to happen. So I'll add in the plus c, and then we'll figure out what it is.
Minus -2.
And so it does turn out that c is -2 in this example, but that's right. It's not always going to be that simple. The reason it works in our case is that the x value that we're using here is x equals 0. And sure enough, when I plug a 0 in for x into my antiderivative, every term except for that c term just disappears. Right? 5 times 0 to the fourth minus 14 times 0 plus c. And I'm trying to match that up with -2.
So if instead of 0 it was going to be 1, for example, it would have been like -9.
Yeah, we would get a significantly different answer if we, -2. So this is c, this equals -2. And so now we know that the antiderivative that we would need in order to continue is 5x to the fourth minus 14x minus 2. And then to finish the problem, we would do this process one more time, but using this initial condition to finish up. But yeah, Luca's point is that if this initial data had not been f prime of 0 equals -2, but if instead it had been something like this, if it had said f prime of 1 is equal to -2, then what I would have done is I would have had to plug in a 1 for my x here instead of 0. 1, 1. And then instead of just plain c on the left-hand side of this equation, I would have 5 times 1 to the fourth minus 14 times 1, that's -9, plus c equals -2. And then I would have an equation to solve for c just by adding 9 to both sides. There I'd get c equals 7. So don't expect that always the number which is the y value of your initial condition is going to be the same thing as your arbitrary constant, capital C. Go through the motions of plugging in the x value and the y value into your antiderivative to figure out how to find that arbitrary constant each time. And And if we were finishing this problem, we would just do that whole process one more time, take an antiderivative of this, and then use this initial condition to determine the value of the arbitrary constant. So this problem number 8, asks us to find an antiderivative for the function 5x to the power negative 1. And then to use that antiderivative as part of a definite integral. So first of all, we can at least milk this problem for the definite integral content. How would I what are the steps in finding a definite integral? Using the fundamental theorem of calculus, what's going to be my thought process here? Yeah.
Find the antiderivative.
Okay. Find an antiderivative. And then what do I do with that antiderivative?
You plug in 5.5 and 1
Yes.
separately, and then you subtract them.
Yes. Great. Evaluate it at 5.5, evaluate it at 1, and then subtract the results.
I'm just confused, like which one you subtract from which.
Great point. So the way that I've written it here is suggestive. So it's the upper limit evaluation minus the lower limit.
Okay.
So the one on the top minus the one on the bottom. Which if you get that mixed up, then it's going to cost you a sign error, which is not a disaster unless you're working for NASA, in which case it could be a disaster. But otherwise, yeah, that's the worst that could happen if you get that order backwards. But the hardest step in the process here for this integrand, for 5x to the minus 1, is going to be the antiderivative step. Because what happens if we apply the power rule to 5x to the minus 1? Well, the 5 just comes along for the ride, right? But what about the antiderivative of x to the minus 1? According to the power rule, what would we do? Add 1 to that exponent, and then what? Divide by that exponent. And that is a problem. Why is that a problem?
I think it would be divided by 0.
Yeah, dividing by 0. Right? That's the only operation in all of arithmetic that is impossible to carry out. Right? Division by 0 is the one thing that we can do to break the number system, right? Using our 4-function calculator, plus, minus, multiply, divide. So clearly, this function is not a well-defined function. X to the 0 over 0 doesn't work. Which is why if you try to approach this problem using the power rule that we talked about in our last class, you're going to hit a brick wall. So it turns out, here's how we resolve this. Here's how we resolve this tension. X to the power minus 1 is the only power of x that doesn't follow the power rule, whose antiderivative doesn't follow the power rule. Doesn't work with the power rule. And so one of the great surprises of mathematics is what happens when we do take the antiderivative of x to the power minus 1. That we don't really have time to talk about why. So for us, for the sake of time, here's what does happen. Call this a theorem if we want to. The antiderivative of x to the minus 1 is actually capital F of x equals the natural logarithm of x plus c. So this should be seen as something of a surprise, right? We're not used to seeing logarithms show up in places where we didn't start with kind of exponential functions and that other kind of behavior. But one of the surprises in calculus, I think, is that there is a relationship in calculus, not just in algebra, but in calculus, between this nice, friendly, just power of x, which is something that we can compute just using the 4 functions of arithmetic, and its antiderivative, which is what we call a transcendental function. The natural log of x is not something that we can compute just by adding, subtracting, multiplying, or dividing real numbers, right? It's this thing that is much more deep and intricate. And so that's the one function which is a power of x, which doesn't follow the same power rule for antiderivatives that the other powers of x do. The flip side of this is that if this is the antiderivative relationship, there's also a derivative relationship that goes the other way. conversely, the derivative of the natural log function. So the derivative of f of x equals ln of x. What would you predict the derivative would be, given the theorem written here? What would the derivative of natural log of x be? X to the minus 1. Or 1 over x, if you like. Right? So this is kind of, again, it's a real surprise in calculus that these two functions, I'm going to call it 1 over x here, and ln of x, that these two functions have this relationship. Antiderivative, derivative. Right. So if you're working this problem in the online homework, then when it comes time to find this antiderivative, your first step in finding this antiderivative is not this time to use the power rule, but to replace x to the minus 1 with the natural log of x. Again, we won't see a problem like that on today's exam that we're doing, but maybe in the future, probably not. This is kind of a gotcha, and I'm not interested in a 2-week intensive course and playing too much gotcha.